All right, let's get started. So we have an exam tomorrow during the lab class, right? The last exam for some of you not, but some of you important graduation. So hopefully it'll be memorable. If not, that's okay. But let's go through some of the topics that are going to be there. And I do have an example of a root locus problem. One of your classmates asked if we could go through one, so we'll do another practice problem. It really is just plugging and chugging a lot of numbers, but laying out the basic root locus and thinking about what has to happen, hopefully will help you sort of understand like how to tackle the problems. All right, so we'll start off with steady state errors, and it's been a minute, right, since we did that. It was before break. But realistically, the whole thing about steady state errors, you're looking at the difference between what you want and what is actually being fed back. So the error signal is the actual input to your controller. And hopefully what you can do is you can minimize that steady state error to acceptable values, or even better would be zero. So the key thing about doing steady state error is identifying the system type. The system type is the number of integrators or the number of poles at S equals 0. And when you do that, you can use this table. So if it's a type, yes, sir?
We're getting everything.
Yes, I think I've included it on the back. This is the one that I made up, just I think it's a little bit easier. I think I made this one up, I can't remember. I think, no, maybe I did not make this one up, sorry. So type 0 system, no integrators. And all you need to do is go down, is you take a look at your error constant. This case, we have Kp, Kv, Ka. K sub p is your position constant. Kv is your velocity constant. And Ka is your acceleration constant. Equations for those are up here. We start off with your position constant, and it's just the limit as S approaches 0 times here's the key thing, open loop transfer function. Do not use your closed loop transfer function, because you need to open the loop up to actually calculate the steady state error. So that's why it's just G times H, not 1 over 1, G over 1 plus GH. Your velocity constant, if you take the derivative of position, you get velocity. So I just have to multiply K sub P times S, and that takes the derivative of my position constant, and then I get velocity. So it's the exact same equation, except I multiply by S. And then to get my acceleration constant, I take the first derivative of velocity or the second derivative of position. So again, it's the same equation for position constant, but now I have to take the second derivative, which in the Laplace domain is to multiply by S squared. Right? So you only need to remember the K sub P term equals limit as S approaches 0, S approaches 0, your open loop transfer function. And then they get the other ones, you just take derivatives, multiply by S. So those are the equations you need. Now we see that K sub P, you can calculate it using this equation. And you're welcome to calculate K sub B and K sub A, but we know for a type 0 system, those are going to be equal to 0. So don't bother calculating those, save yourself some time. And then the last thing we need to do is take our steady state error and actually calculate the error given our position constant. Most of the time, the input's going to be just a unit step function. But if it multiplies by a magnitude that's not unity or 1, you'd put that up here. But otherwise than that, our steady state error is 1 over 1 plus K sub P. Because my steady state error, when I do my limit functions, the one term that we see over here drops out. And I'm only left with 1 over K sub B for my steady state error for a ramp input, and the same thing for a parabolic. When I do that, I put 1 over 0 is infinity and infinity. So for type 0 system, just look at the table. Type 1 system, look at the table. In a type 1 system, you know that K sub P is going to be equal to infinity, which means your steady state error is going to be 0, which makes sense. Because if you're trying to keep up with something that is constant in its input, the only way you can get to that is if you have at least one integrator to take out the error. my velocity constant, I'm ramping up. So if I integrate once, I can get a constant output, but I can't catch up and get to that same ramping input. So I'm going to get a constant error. A parabola input, it's too much, or not elliptical, but a exponential input. I can't get that from here. I can never catch up to it. So over time, I'm going to have an infinite steady state error. And then for a type 2, you've got 2 integrators now. Now you can really work hard to keep up systems. So for a step or a ramp input, I can force those outputs to be 0. For a parabolic input, or again, an exponential input, I can try and keep up with that, and I almost can, except I'm going to get a small amount of error. And I calculate that error using my acceleration constant, and I have 1 over k sub a. Okay? Questions on that? Really, it's just using that table. If you have non-unity feedback, don't worry about it. Just include it in your open loop gain, your GH. Questions?
I mean, that's the H.
The H is the feedback. Yep. That's the feedback element. All right, no questions, then let's talk about polar and rectangular math. Remember, we spent half of a class just doing multiplication, division, addition, subtraction of complex numbers. And that's the polar and rectangular math. We can always go and we can always do this. We can do anything we want when we write it in rectangular coordinates. We can add, subtract, multiply, divide. We can always do that way, okay? But if we have magnitude and an angle and another magnitude and an angle, we really can only multiply or divide, right? We can't add and subtract magnitudes and angles easily. We just don't know how to break up those components. So we can't add or subtract vectors like that. It doesn't work so well for us. But multiply and divide is a real piece of cake. So what we do, if we multiply or divide, we either multiply or divide the magnitudes. And the angles are going to be either added or subtracted to get that. So that's just kind of summarizing what we've done. You probably did a lot of this when you did AC circuits, where you did a lot of complex math. But we like to work in this class in polar numbers because we have a transfer function that has a bunch of zeros and poles. And when we're trying to solve for magnitudes and angles, it's much easier to use polar quantities. So that's the reason why we spent a little bit of time kind of reviewing polar math. And we see here that we can get this magnitude of this k. We know that that magnitude of k is always going to be 1 over GH, magnitude only, because k here is a real number. All right, so the whole concept about a root locus is we have to always make sure that the result of a valid root means that GH evaluated at that valid root, so we'll put at S equals a VR, has to equal 1 at an angle of plus or minus 180 degrees. Okay, so if you have a valid root, if you want to solve for your value of k, that you got a valid root, you can just use this equation here. Now, number 3, in my opinion, is the key to root locus, the starting and the endpoints. Because if you can lay out a root locus, at least initially, what it looks like, and get a little bit of insight as to where the root loci go based on that initial setup, then you don't have to calculate a lot of these other parameters. Like if you never leave the real axis, do I ever need to calculate angles of asymptotes, breakaway points, any of that stuff? Don't need to do it. Don't need to do a root locus, Ruth Hurwitz calculation either, because I'm not crossing the j omega axis other than maybe crossing it at 0. So I don't need to do a lot of that stuff. I can simplify my life. So remember our mantra, a root locus starts at a pole and ends at a 0. They don't have to be finite zeros. And in many cases, we'll actually have infinite zeros, but that's okay. But we will always have finite poles. We should never have a system. And have you seen an example where I've done one where we've started at infinite poles? Doesn't happen. The real world systems don't have more zeros than poles. So once you've figured out, the general form, now you can start to figure out, what do I need to calculate? If I have some angles where I do need to get away from the real axis, so I have poles that are going to be leaving, or roots that are going to be leaving the real axis, then I might need to start calculating where do they approach s equals infinity. So I need to calculate the angles of the asymptotes because I need to know how that root locus approaches it. Here's the equation here. And then the starting point for that, the angles of the asymptotes, I need to calculate that starting point. So that's my sigma sub n. If I have poles that are leaving the real axis, or roots that are leaving the real axis, then I've got to go ahead and calculate the breakaway points. If I have poles or zeros that are finite and that are not on the real axis, now I start calculating departure or angle points, so I know what it looks like either to leave or to approach a pole or a zero, complex pole or zero. So then I'd have to calculate theta sub d or theta sub a. And if I have a root locus that I need to calculate, then I'm going to go ahead and that crosses the j omega axis, then I can use my Ruth Hurwitz to calculate it. This is the table that I created. So I did it slightly differently. You can give me your honest opinion as to what one you like. I just tried to do it a little bit more efficiently. Maybe I over-defined it, but I put everything in this table. So I put the K sub P, KV, KA. I also included K sub J, which is jerk, because there was a student who graduated many years ago who was really into high-end RC cars. And one of the things that I guess was a performance characteristic is how fast something can accelerate. That's called jerk. So I included it in here. So I added a type 3 system. And then you can see where all the steady state error, the step input, that type of stuff, you can see all that stuff is laid out in the table. So it's exactly what we saw previously. This, I just tried to put it in a more concise table. You can most likely neglect a type 3 system or a jerk system, but it really is just expansion, just to take the third derivative of position. So you'll get that, and then you'll get this. Those are the summary of how to calculate those terms. Just be careful. I gave you a slightly different approach to calculate breakaway points. You are welcome to use this one. Some people find this one easier if you don't like doing derivatives, or if not, take the derivative and set it equal to 0. I like doing derivatives because calculus is super challenging in some cases. This one I find that there's just a lot of algebra. So for people who are really hell-bent on avoiding calculus, you can do this. Questions? Really just two major topics, right? Steady state errors and root locus. I do have a root locus example that I'll put up just because, like I said, one of your classmates requested it, but Drew, you have a question?
Yeah, on the homework, I was kind of spacing out how to find if there was a positive or negative 0. We just run over that pretty quick. I know that's kind of.
Well, a positive or negative 0 at s equals infinity. The only way you know if it's positive or negative is when you draw your root locus. Is it, so let's put up an example.
I mean, number 2 is kind of like.
So remember the rules, right? It always lives to the left of an odd pole or 0. That's on the real axis, correct? So you can only have one over here because this is number 1, has to go this way, right? So if it's anything on the real axis, Unless, again, you have something like this. Now the question is, where are my poles and where are my zeros? So what you'll need to do is, if you only have two, you're going to have to actually break away. And then if you reconnect over here, you'd have two over here. And how do you know that you have two on the left-hand side? Because your break-in point is right here. If your break-in point is over here, then you have two positive roots at s equals infinity. So to the best of my knowledge, there's no way of calculating if the infinite zeros at negative or positive numbers, because remember, we do have some cases where we had this, right? So those would approach positive zeros at s equals infinity. And that's again, because you just need those because of this angle of the asymptotes that's plus or minus 45 degrees. So it has to go in the positive direction. So there's no way of telling other than just looking at it. But that's the nice thing about it. It doesn't matter. It can either be positive or negative. You just need to go ahead and set up your root locus to figure out, oh, how do I close or how do I finalize this root locus? Well, over here, they've got to be way out over here. So that means they're at positive s equals infinity. But in this other case, they met the criteria to be at negative infinity. Okay. So like I said, there's no way of knowing that I know of that you'd be able to determine if they're in the left-hand half plane or in the right-hand half plane. You've got to look at the rest of the information to be able to make that determination. Questions? You want to do an example? Root locus? All right. Given my open loop transfer function is k over s times s plus 3 times s squared plus 2s plus 2. Draw the root locus. Fair? All right, so the very first thing you should do, this is just my approach, what are the poles? I know I got one at 0. I got one at -3. This one, I don't have it, so I'm going to do the quadratic equation first. So negative b plus or minus the square root of b squared minus 4ac all over 2a. Nope. 1, yeah, sorry. I was going to put the 2 over 2, but I'll.
I know.
Huh? You love MATLAB now?
I do the bridging for MATLAB.
Yeah, you can do symbolic stuff in MATLAB. And...
Yeah, simplify it. Because double is more complex problem. There's no possible way. No,
You can't get it.
You just got to look around, yeah.
feels together.
Makes it too easy. Maybe I should not make it available. So those are my poles, right? -1 plus or minus j. What are my zeros? None. I don't have any zeros. I can't even write 0, but I can write none. So immediately what I know is that n, which is the number of roots of the denominator, is equal to 4. And the number of roots of the numerator, or zeros, is equal to 0. So my r value is going to be plus or minus 1, ... plus or minus 3. And remember, it goes all the way up to plus or minus n minus m, right? But I can't go past 3 because n minus m is 4 minus 0 is 4. And the only way I can get to 5 is this m minus m is greater than 5, right? 5 or greater. So all I have for my value of r, plus or minus 1, plus or minus 3. So now I'm ready to go ahead and start to draw the basic pole zero map. And I'm just going to go ahead and write my poles and my zeros. So here's my X. Here's my X. Here's my X. Oh, maybe that's a little too high. Here's my X. And here's my X. Okay, that's the base root locus plots that I have. And so at this point, maybe one additional step is to draw all the real axis pole and zeros. I mean, the root loci. Well, I know it lives to the left of odd or even poles and zeros. So it's going to live here. Can it live anywhere else on the real axis? It cannot. So I know that I will not have any asymptotic angles at what? No, the angles, the actual degrees. I know the angles of the asymptotes cannot be plus or minus 180. Why can't they be plus or minus 180?
Yeah, only the axis somehow.
I'd have to get off the axis, which is okay, but I'd have to get back on the axis and approach a zero at s equals infinity. But this tells me that I cannot be back on the real axis because the rule is it only exists to the left of an odd pole and zero. The only way that that would make sense is if I had two zeros out at s equal infinity that were on the real axis, but it's highly unlikely that that's going to be the case. All right, so now we know that we're going to have some asymptotic angles, and they're most likely not going to be plus or minus 180. So let's go ahead and calculate theta sub A, the angle of the asymptotes. And we can go back over here and use this equation, r times 180 over the number of poles minus the number of zeros. So that's going to be equal to r times 180 over, and I'm just going to substitute this in, 4 minus 0, right? Number of poles minus number of zeros. So r can go plus or minus 1, plus or minus 3. So I'm going to have to calculate 4 asymptotic angles. So for r equal to 1, theta A is going to be equal to 180 divided by 4, which is 45 degrees. For r equal to minus 1, theta A is going to be equal to minus 180 divided by 4, which is minus 45 degrees or 315, right? 40 minus 45 is the same as 315. R now moves to positive 3. There's going to be 3 times 180 is 540. Divided by 4, which I calculated out to be equal to 135. And R equals 4. Theta sub A is equal to minus 540 over 4, which is equal to minus 135. Sorry, I don't know why this does this. Minus 135, which is also equal to positive 225. Questions on that? The only reason why I calculated these asymptotic angles is I have some zeros at s equal infinity that I have to approach. So I need to calculate that. If n minus m is equal to 0, you don't calculate theta sub A. I mean, yeah, you gotta be careful, not the angles of departure, but the asymptotic angles. So I got 45, 315, 135, 225. Those are my 4. Now I need to calculate the center point, the sigma sub A, which is the finite poles the sum of the finite poles minus some finite zeros divided by n minus m. So sigma sub A is the finite zeros. Or is it finite zeros or finite poles? Finite poles. So I'm going to sum those, and I have 0 plus minus 3 plus -1 plus j minus or plus -1 minus j. That's the sum of the poles. What is the sum of the zeros equal to? 0, there are none. So that has to be equal to 0. And then I divide that by n minus n, which is equal to 4. Now, here's the other thing about wanting complex conjugates. Remember what sigma sub A is. That's the location on the real axis where your asymptotes center. The plus and the minus j have got to cancel out, because if they don't, then I'm not on the real axis, right? So what I see is these cancel out, and I'm left with -3, -1, -1. So -5 divided by 4, which is equal to 1.25 negative. So all 4 of those angles start right about here someplace. And they go at 45, -45, 225, and 315. So going back to Drew's question, do you start to see now perhaps where you have zeros at s equal infinity being on both sides? Some approach it at a positive value that result in roots on the positive side, and some are at the negative side. Okay, questions? Am I going too fast?
So the sum of four, right? So you put the minus three, which is.
I'm just summing these actual poles, so just sum those right there.
Oh, okay.
Because I'm not looking for the original equation. I'm actually looking to sum all the actual poles. The poles here are -3, 0, and -1 plus or minus j. So just sum them together. All right. So am I done? Have I done all my work?
But it's possible that you can find 2 points where where it leads from the relaxers. If you just find 1 point, which is 1 point. Possible.
No, you'll always have the intersection will be at 1 point. It's only 1 point. But again, that's not where the root loci lead. That's just the angles that they approach at s equals infinity. So the root loci don't even need to pass through that point. They just happen to pass through here at this point, but they don't actually need to pass through. It's just what are those angles they're going to approach at. Okay, so am I done with my root locus? I've got some of it, but do I have all of it? Why do I need to find breakout wave points or break-in points? I don't need to?
I think you find the angle of departure. You can get off of it.
Well, let's go back to the question about breakout points or break-in points. When do I need to calculate breakout or break-in points? When it leaves what? The real axis? Does it look like the root loci need to leave the real axis?
Yeah.
Does leave the real axis, so don't I need to know where it's going to leave the real axis? Yes. I need to know where it's going to leave. So I do need to calculate that sigma sub b point. How do I calculate what that sigma sub b is? Take the derivative of my equation with respect to s and set it equal to 0. What's the equation that I'm taking the derivative of? Well, ultimately, I'm going to solve this equation for k. Why is this being so difficult? It's the equation 1 plus K times GH has to equal 0. So my equation becomes 1 plus K. Oh, this is really slow, sorry. Over S times S plus 3 times S squared plus 2S plus 2. That's equal to 0, so I'm going to solve for K. My K equation is equal to, and sorry, this is acting really funky, minus S times S plus 3 times S squared plus 2S plus 2. Now I got to take the derivative of that. Now it's totally up to you. Whatever you like to do for derivatives, if you leave it in this form, you're going to have to do a lot of is it the quotient rule or is it the chain rule? It's when you take the derivative of the first, keep taking derivative, derivative, derivative. Other people would find it easier to do S squared plus 3S times S squared plus 2S plus 2, right? And then continue expanding it. The only problem with that, though, is, it's easy to miss terms when you start to get to this many terms. So I would probably just set it up to here, and then I would just take the derivative of this, unless you're really confident with the quotient rule, and then you can just, take the derivative of the first one. So now I'm going to take the derivative, dk, with respect to S is going to be equal to the derivative. So the nice thing is there's no denominator, right? In numerator, it's just the quotient rule. So the derivative of negative S squared, this is 2S plus 3. Then what do I do now? What's my next step? Right?
Drop the negative.
No, it's right up front. It kind of got blended into the equal sign up here. So
Oh, I see.
let me move it out of the way.
So I was doing the homework. I was looking at the slides and it looked like the example of this on the slides. The negative sign was, I don't know where it went.
You want me to show you where it goes?
In the one in the slide,
Disappears? Does it disappear?
it looked like, I don't know.
I'll show you it doesn't disappear. Math is a wonderful thing, right? So then plus that equals 0, right? So this is the answer Juice question. What happens to the negative sign right now? What if I multiply both sides by -1? Goodbye, right? So does it really disappear, or is it just an algebra rule? All right, so now, you got to keep expanding it. I've done that for you a little bit. And I have -4 times S cubed plus 3.75 S. Wow, this is really get some lag. Plus 1.5. Boy, oh boy. And that's going to equal to 0. Again, the 4 drops away. And how do I find the correct value of S? What's that? I would probably use MATLAB. I'd put this in and find the roots, right? Because if I get the roots of this, then I know that one of those is going to make that derivative equation be equal to 0. So my roots, 3.75 times, oh yes, S squared. Yep. So now my roots are minus 2.3 and negative 0.725 plus or minus. Okay. So can I tell which is the breakaway or break-in point?
Here on
Pardon?
the breakaway.
Why? It's the only one that's on the real axis, but it also has to meet the criteria that it's between -3 and 0, right? So the root loci break away somewhere around -2.3. Okay. So based on that information, can you approximate where the root loci is gonna go, at least for the ones that on the real axis? Probably gonna go this way, right? And the reason being is because you're to the left of the asymptote central location. So if you're gonna approach it at plus and minus, or plus 135 and plus 225, then you're probably gonna want to stay to the left. So those two leave that location. What about the other ones? Well, I have to leave two complex poles, correct? Correct? Not correct? So I have to calculate the angles of departure. We'll calculate one for the real pole. So we'll calculate the angle of departure for P equals -1 plus J. Everybody okay with that? So I'm going to just highlight this again to make it easy. So I want to calculate the angles of departure for here, remember? And what I need to do is I need to get a point as close as possible to that. Right? Just getting ready to leave that point. So it's basically right when I start is the point I'm going to use, basically when K is equal to 0. So I need to calculate the angle here, the angle here, and the angle here. So this angle is from here, this angle is from here, and this angle is from there. Make sense? Don't make sense? Let's start with the easiest one. What's the angle right here? Oh, wait a minute. Let me get you the equation that we're going to implement. So we're doing this departure angle. It's the theta z's minus the theta p's plus r times 180. So the angle of departure is equal to the sum of the theta z's minus, make sure I get that right, theta p's sum. And then that's plus, we'll just put in the 180 degrees. So this is equal to 0 because I have no poles. I mean, no zeros. So I know that's equal to 0. Now I'm going to go ahead and take care of this one. So that's minus 90. Pretty easy, right? Not right, right? Then I'm going to go ahead and calculate this angle. How do I calculate that angle? And can anybody give me the rise over the run? Remember, this is at -1 plus J. What's this point right here? All right, so go ahead and calculate it when it needs to be. And when you say rise or run, be careful. Remember, it's Sakatoa, right? I'm trying to calculate this angle. The inverse tangent of Oscar had a heap of apples. So it's the opposite, which it rises 1 over the adjacent, and I have to go 2 in this direction, right? To get to that point. So it's the inverse tangent of 1/2. Correct? Not correct? All right, so I only have one left to calculate. How do I calculate that angle? Going to use our A tan again because we know what they are. So A tan of the, go ahead.
I think it's this way. When you the back angle.
This angle right here?
Yeah.
That's okay.
Then you add.
Let's go ahead and take the inverse tangent of the opposite over the adjacent. I'm not arguing, you're right in saying rise over run, but I'm just being a stickler because when we say rise over run, you start to forget the fact that it's all based on, this is just right triangle math, right? So it really is the opposite, which is 1, over the adjacent, which is -1. Yeah, it goes in the negative direction. All right, got all my angles, correct? Do I have all my angles? Survey says, no, I have this angle. I need this angle. So how do I calculate that angle? Boy, oh boy. This is really slow. And don't forget, it's going to be subtracting this angle, correct? Not adding. Because the full 180 is to go this way, and then I have to back up that angle. You see why it's important to draw this? Like how helpful it is to draw this out? And when you do that, you should get, what did I get? 71 something, minus 71 something.
There's still another plus 180.
Oh, yeah, sorry, plus the 180.
Just one. So how do you know the R for that? Yeah, that's one.
It's based on the number of poles and zeros you're going to be leaving. So you only have 2 that you're going to worry about. So it's the plus and the minus 1. You've only got 2, right?
So
You don't have to calculate 4 departure angles because you've only got 2 complex poles. And that's going to equal minus 72. So now I know, going back up over here, and this again is another suggestion. I know that I'm going to go off at minus 72, so I'm probably going to curl down something like this. And this, because of complex conjugates, going to probably do something like that. All right, now do I have enough information? Now am I done? You said you wanted an example. Yeah, very good. We can still do the Ruth Hurwitz to get the J omega crossings, correct? So how do we do that? We do the Ruth Hurwitz. And if you remember from our characteristic equation that we worked to get the derivative one, multiply that out, that's s to the 4th plus 5s cubed plus 8s squared plus 6s. Wow, boy, oh boy. Plus k. That's our actual characteristic equation. So we have s to the 4th row, s cubed row, s squared, s1, and s0. Question? That's the characteristic equation. If you remember when we did the d sub k equation, if you do this right over here, this one right here, sorry, and you set that equal to 0 like we have here, that's the numerator of the characteristic equation, or that is the characteristic equation. So if you multiply this out and add k to that, you get this. K is right here. It's right here. It's already in there. Remember, this is a gain constant. It's multiplying the gain of the system. So it's 1 plus k. It's built into my block diagram. So I have a k here. The characteristic equation is the closed loop. And this, the 1 plus kgh, gives me the closed loop transfer function. So this is g. And I'll just put a unity feedback here. So I'm getting the denominator of the closed loop transfer function. That's what the characteristic equation is.
So from here, got that one,
Pardon?
from this equation,
The one that I've highlighted?
yeah,
Yeah, because remember the closed loop transfer function, G closed loop is equal to G over 1 plus GH. In here is K G, right? So it's 1 plus KG. It's really slow. I don't know what's going on. That has to be set equal to 0.
so you kind of find the one plus kg for there.
Yes, that's this is the characteristic equation. This here is the characteristic equation. That's what we do Booth-Hurwitz on, right? Is the characteristic equation.
And then the 1 plus k over s.
Right here.
Yeah.
Yep. What about it?
What's, how would put it in relative to the equation?
Well, then, so remember this right here, this whole thing, this 1 plus K over S squared plus 3S times S squared plus 2S plus 2, right? That's what the denominator looks like. When I put them under a common denominator, this is going to move up here. And then this whole denominator, when I invert and multiply, is going to get put up into the numerator. It's going to cancel some stuff out. So I only really care about the numerator of the denominator. That's the characteristic equation. Do you want to do the whole thing? Let's do the whole thing. So this right here, this is the G over 1 plus GH. Might take an hour because my computer isn't responding. Right? That's G over 1 plus GH. So now I'm going to do common denominator. I'm just going to put brackets here, and this becomes, let's see, S to the 4th, right? Because S squared times S squared is S to the 4th. Then I have 2S times 3S. I'm sorry, 3S cubed plus 2S cubed should be 5S cubed. Right? Plus, now I have, let's see, I've got a bunch here. So this is where it could get more confusing. So I have 6S squared plus 2S squared, and that's it. 8S squared, if I did that correctly. And now I have 4S, or sorry, 6S, and that's it. And then, so that's multiplied out, and then that becomes plus K, is my last term. And that is all over this denominator. When I invert and multiply, these two cancel out, and all I'm left with is this in the denominator, which is what I did right here. Ready to do Routh-Hurwitz? 1, 8. Right? 1, 8, and K, yep. 5, 6, and 0. Wakes up. All right, so I've got to work it through, and all I really need to do is go to the S1 row, right? I need just a row of zeros. So my next terms are going to be, let's see, so I have -1 over 5 times, now you know my determinant, so 6 minus 40, oh boy. So let's see, I have -36 over 5. Oh, positive, yep, thank you. Okay. And then I know my next one, what's my next term going to be? Don't even need to calculate it, right? Because that zero term is going to drop out. So I'm going to be left with K. My next one is now moving down a row. So -1 over, well, actually, I'll just put -5 over 36. Anybody have any heartburn with me doing -5 over 36? Because all I did was -1 over 36 over 5, and I just inverted, brought it up. So now I'm going to do the determinant. So I have 5K minus 6 times 36, which is 180, 216 over 5. 34, okay. So, sorry, I had a typo. Yes. Why did I say 36 when it's 34? Doesn't want me to write 34. Hold on, some technical difficulties here. It seems like whiteboard has fallen asleep. All right, let's try that again. Seems to have woken up. All right, so 6 times 34 is 204 over 5. And we don't care about the next term, right? That doesn't matter. So all I really care about now is this term right here, -5 over 34 times 5K minus 204 over 5 has got to be equal to. Everybody hold on a second. I'm just going to see if there's something running in the background that's eating a lot of resources, because it's really hard. It keeps tripping on itself, and I don't know what's causing so many issues. I mean, obviously Zoom is taking up some resources, but
No, Jen's been having troubles with and slideshow PowerPoint.
yeah. Well, I'm going to free up some resources here by, I don't want to end MATLAB. So I cleared up a little bit of memory by shutting down a bunch of stuff. But no, it's running antivirus, so it's taking up a fair amount of resources. So let's see if I close up a bunch of things. Now I have 60%. Maybe that'll work out a little bit better. When I do that for my Ruth array, I see that. Oh, maybe I made it worse. K doesn't seem to make a difference, equals 8.16 is where it crosses. And so when I plug in K equals 8.16 into my auxiliary equation, 34 over 5 s squared plus, sorry, 8.16. That's going to equal 0. So my S is going to be equal to, I'm really sorry, this is just not seemingly working. So I'll just have to paraphrase as much as I can, because it's really, I'm going to have to restart the computer again. But so S is going to be equal to plus or minus, you can see it's just really bogged down, J times 8.16 times 5 over 34. And that's where it crosses the J omega axis. Like it's just not working. So
8.16s or
what's that? 8.16 is the root. And
None of the auxiliary equation, you put s squared. No s.
no, that's the idea of an auxiliary equation. Remember, it starts in row S2 So that's the S squared coefficient. Then you skip a coefficient. So you skip the S1 coefficient, doesn't exist. And then you move to the S to the 0 coefficient, which is K. And so this is where, and again, I'm really terribly sorry that this is being so darn difficult, but it's just really hung up. So it crosses at that value someplace over here. Goes like that.
But then now you ask to find the value of K at which the damping control when it's on like
Yep.
how would you go about it?
So if I know a K that I want, let's say that my damping ratio gives me over there. Right? I have that value. So that's a valid root. So your value of K is going to be equal to 1 over GH evaluated at S equals whatever that point needs to be. Just solve for the value.
That's the thing. That value, that's the thing.
Yeah, so remember the damping is you've got these lines that go up like that. Well, maybe they don't go like that, but that's that whole thing if you looked at the beginning of the root locus where you would calculate those angles or the settling time. We did a lot of that when we looked at second order systems, but we reviewed it at the beginning of this chapter. So that's where you pick the points.
Can you cross over the asymptotic line like that? Where you show your lines coming off of the wall?
Sure. The asymptotic angles just tell you what it looks like as it approaches infinity. You can cross it once, probably only once, but yeah, you can cross it.
And then is there, like, the last question for you on the homework, it was what gain gets you the sort of damping value? So I actually got lucky, I put it in MATLAB, and the first point I clicked on was 7.0 or 0.707 damping coefficient, so that just had to be.
That's because you picked the point, but you should be able to calculate it with this. You should be able to look at your plot, calculate what that angle needs to be, or what the angle is, and then approximate the point what needs to be, and then calculate your value of K based on that root that you've got. That's what we just did right here. So you can't use MATLAB and say from MATLAB, K is equal to 2. You've got to show me how you would do that. If you want to check your work in MATLAB, that's fine. No, I don't know.
So,
Yeah, I don't remember.
no, so that's what S is equal to 1.
Whatever, if this is a point that you want the system to respond at, so you've got all these lines that you've drawn on your root locus. So you've got the root locus, and then you've drawn what my zeta value needs to be to meet my percent overshoot. So you picked, all right, that point is going to give me satisfactory overshoot as well as settling time. So I know that root is good. So once I have this point selected, then I plug it into this equation right here and evaluate for K.
So do you mean that I get that one? That's how you know what groups.
The ones you draw, you can calculate them. Can't you calculate them from this? Yeah, it's like the first or second slide. Third slide. Here.
I don't know. You said that looking at it on like right here.
We derived this already, remember? We derived this quite a bit in second order systems. This is just a summary. It's not much. You know that zeta here is the inverse cosine. Take the inverse cosine of zeta to get that angle. And then the settling time is determined from here. That's why you have this summary slide. It tells you all the different things you need to know for design. Yeah, you were harassing him and he's like, yeah, thanks. I don't know, I'm not hearing anything, so
Can we just make it the final?
make it to the final.
Make this the final. Push this to the.
So you want to have all your grades based on these 3 exams?
No.
I don't think that that's allowed with university policy. The syllabus is already written, so I can't do that. I'd be cheating you out of a good experience.
It's funny if people just have things that they do, it's like, oh, you're happy with your exam.
Last 50%. Why would you want to stand here?
I don't know, I understand a little bit. So let me just say this. So the reason why I do the final and I make it mandatory, it's actually more work for me, isn't it? But it can be more work for you, but the reason why I do that is it's like you paid for 15 weeks of the semester. If you did well in this test, what would happen? Nice knowing you, Paul. I'm not coming to the rest of the classes because I'd be done. So you're kind of not getting what you paid for if I allow that. So I know it seems a little unfair, which is you paid for something and I'm making you do more work, but the hope is that you're getting more learning.
So what if I do class for a semester? What already comes in the first day of class?
So, I mean, just look at it from my perspective. I really am trying to make it so that you're getting the full value for this. I'm not trying to cheat you. And I know it might seem frustrating and like I'm actually being a hard ass about it, but this is my own personal thing. I just feel like I owe it to you to give you what you paid. And if there's a little bit of extra learning, like we'll cover a little bit of Bodie plots next week, but a tiny bit, just because again, you paid for it and you can just see how really useful root locus, S-plane stuff is to make Bodie plots really simple. But I know that that's not always a popular opinion, but remember when I said my family was in Florida over March break and I was here, and I'm like, I don't feel like that's right to take away. And you're like, oh, just go, don't worry about it. We'll figure something out. But it's like, you guys paid for that time. It doesn't seem fair to you to take off. I'm not judging anybody else. That's just my personal beliefs.
So on the exam, how much do you want us to show on our paper and put it in that?
I don't want to,
Like if I use the calculator for
you got to do the derivative yourself.
I pulled on the paper.
Yes, because MATLAB is a calculator. Right? Most calculators can't take derivatives.
Yeah.
And the ones that they allow you to use on the FE certainly can. So I want you to be able to understand the theory behind it and the concepts. And it's, tended not to be very difficult derivatives, right? The derivative we did here was not super difficult.
So you're gonna leave it like the question 3 derivative or the question 2?
You got 3 hours, right? So
Yes.
why was it really that hard?
Yeah, that's really.
No, I mean.
But if you're taking a derivative, you throw out the numerator. You don't even care. The numerator goes away, so you don't have to worry about it. You just do the multiplication. Pardon?
The derivative,
You mean the column?
yes.
Yeah, throw out the denominator. Did I say numerator?
Yeah,
Yeah, you just trash it, so you don't even worry about the math there.
but yeah, it's the easiest part, but you're multiplying S squared plus 4S plus 8 by 3S squared plus 14 plus 10 minus 0.5.
Foil it. You can always do foils. You can just do the arrows. Dinky, 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 just do arrows, right? Color coded arrows. That's what I would have done.
When you have 2 polynomials, so there's 3 terms, so you just multiply each term by each term.
It's foil, but you don't do foil outer inner last. What I do is first, I take the first and I multiply by 3 terms. Then I take the second and multiply by 3, and then the third, multiply by 3. And then I just line things up with S squareds, S cubes, whatever. And I just basically make it like, here's how it lays out. So if I'm doing 2 by 2, and even sometimes 2 by 3, I oftentimes will just try to do it in my head, but sometimes I make mistakes. But you can always go back to like, you know what, I'm going to multiply the first number by all 3, and the second by all 3, and then the third, and then just align your terms. It's not too bad. Literally, I will put them up in rows. So my first row will be my first coefficient. Then I'll move down a row and I'll try to line up the coefficients with the S squareds. And then the third, I'll move down another row and then line up all the coefficients. And then you just literally, you go down vertically. It's pretty simple. You just haven't done it in a while, right? So that's why it seems hard.
Oh, yeah.
But if you really feel strongly about not taking a final, if you don't feel like that adds a lot of value, we can discuss it after the test. How's that?
Yeah, after the next.
let's see. Because again, so one of the things too is I have to look at you as not only students, but also as a little bit as peers. So it's not a one-way street. I am open to feedback, conversation. Something's too difficult, something's too easy. You also have an opportunity to do feedback on the, I can't remember what those, the blue, whatever ones. But the thing is that feedback is after the fact. It's way better for you to come to me and say, hey, can you do this? Can you think about this? And as long as it's unprofessionally, like, I think this is a little unfair. I think this is too difficult. Will you adjust it? I'm going to be much more open to that than you screwed up and you're a jerk and all that stuff. You know, don't put people on the defensive. But if I'm doing a bad job at something, you can say, look, this is not the way that we want this. It's way better to do that with me than to wait to the end of the semester. And we, as all faculty, if people have complaints about one faculty member, we will always tell the students, you need to talk to that faculty member first. And the reason why you do that is because you're learning a professional skill, which is how to cope or how to deal with difficult circumstances. It's like, you heard the term helicopter parenting. If your parents always come in and help you deal with all these issues, and then you don't deal with them, then when you get out in the world, then you got to start dealing with them by yourself because your mom and dad is not around, or whoever, you know, what you want to say. I don't mean to genderize things, I apologize, but your parents aren't there to help you. So the concept there is you need to be able to do some of these on your own. So for me, with my kids, you know, I have one kid that's really into sports, and, you know, try to help him from the bench and all that stuff, but he's having an issue with another person on the court. I'll just, you know, stay away unless somebody's getting physical, and then I will try to pull my child out of there just because I don't want them to get injured. But it's more about, you know, you need to figure out how to resolve it. So it's resolutions, and that's the same thing when you're dealing with a difficult one. I would hope that most faculty here would be open to comments, constructive criticism. But I can't guarantee that's the case. Yes.
Well, if
You
the
get zapped?
yeah,
Oh, I was gonna say, I hope it's not hot.
the because by here from schools,
Yep,
if you find this
yep.
how do you find this point where the intersection?
Where it intersects,
Yeah,
you've drawn the root locus. So you know that it intersects here, right?
yeah.
That's what I was wondering.
You're gonna have to read it off the graph. You have to have a graph that's accurate enough to read it, or just draw by hand. If you need to do MATLAB, that's okay. But normally you can get close, that you can eyeball it. Again, you just have to be close. You don't have to be exact. If you're off by a little bit, it's not a huge issue.
Because I'm like, maybe you might, I don't know. Yeah.
You just have to eyeball it.
Okay, because the other way would be.
So another thing is, if you're wrong, if you're way off, plug it back into your characteristic equation and see if you're gonna get valid roots. So pick that root and plug it in there and see if K equals, well, if you get plus or minus 180 degrees, it's the best way to check.
Because only if you give us those kind of two, that would be. So if you give us the dumping ratio and the point, then we can find this point.
Yeah, but generally speaking, I'm not gonna tell you, you know, make sure the percent overshoot is 25%. I would say make sure it's less than 25%, so you can do anywhere here, right?
Somehow.
You can calculate it based on here at a fixed damping ratio.
Yeah, so that you can calculate what that point is, right? So
Right.
Because if you know your damping ratio, you find your and
Correct.
then from you use your characteristic equation, right? To
Yes, yep,
But then find your omega n,
yes,
and then you can just do cosine, sine, and find your x and y.
correct. Yep.
But then you don't have to see that.
No, your measure of n will give you this.
Yeah, omega sub n gives you the entire length. It goes to that. He was talking about a point not at omega sub n.
Unless if they match. That's
You need at least two pieces of information. You need to know what this length is, you know, whatever that value is, or this length, or this length. The only thing you have is the angle.
the
So you're missing one piece of information.
You need to just guess.
Well, not guess, how about eyeball, approximate?
Yeah,
Guess makes it sound like you're just doing this.
oh, yeah, approximately. But then I think. This is fun, yeah.
Instantaneous.
Because the one from the homework, it does this, listen to your angle.
Yeah,
And then it's one here,
yep,
and then I can just sit up from the K, but then I was like, I'm supposed to calculate it.
you just have to estimate.
Which means in the text, I can just find the angle, go to much level, get the K, right?
Yeah, but remember, you gotta draw this by hand, so if you say, from the plot, I can't get the resolution enough, but I should be able to, I wanna see how you could calculate the value of K. It's okay if you said, I can't draw root loci for beans.
Yeah.
So you can say, I got from root loci 2 valid points, and then you can show me how you got those points to get the value of K. You can't just read K off MATLAB. I wanna see you calculate it.
Yeah, I can get, if I have, yeah, I can get the point for what level, so I can back.
That's fine.
Yeah, like on the homework number 310, where it comes over that splits out three number. We didn't find anything that tells you how far up it goes, so you could draw that in a number of ways with that loop coming off. So then if you do this, I don't know,
Yeah, I mean, yes, you're right. So you just have to have practice just drawing them. So it's not ideal. But you know what you can do? You want to refine it. How would you refine it?
What do you mean?
He was saying, I've got, the homework was something like this. I don't know about halfway through. But he's saying here, 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 and here. Does it look like this? Or does it look like this?
pick a value somewhere in the middle there.
Try K equal to 1 or 10. To do it right.
Fine.
Just try a bunch of different values of K, see what you get. All these points here are determined on those values of K. So if you're not sure what it looks like, try a few points. It doesn't take you long. Once you have your characteristic equation, it's a function of K, right? So you can just make MATLAB, or even in your calculator, you can just say K is equal to value, and then hit roots of that equation, and then you'll get it that way. So you could do that really quickly that way. That's the only way that you could refine it, is something like this. That's what MATLAB does. When MATLAB plots the root locus, they just run a zillion values of K, and then they come up with points. That's how MATLAB works, because that's all it can do. But if it's not your last coefficient, that's what we saw at the end of the chapter. You have to tweak it a little.
Yeah, cool, but then also about the thing we had just when we do the columns. So the graph was here, so it does this. So it seems like the angle of 45 degrees, the when you zoom in on that like 0.5
That's okay.
time is really the right angle.
Yeah, it's supposed to be right beyond that point.
Yeah,
It's the angle.
so you're right.
So it has to be really close to where that point is. That's why you can actually calculate those angles at that point. So you know that those poles are right physically at those points. So that's why you're trying to calculate.
Yeah, right there, like.
Yep.
When they go out, it should do infinity.
Yep.
So just, so it seems like, 45 degrees when it's.
Just leaving the point. But then you can find a few points to see if it curls around if necessary. You can write your own MATLAB script to do root loci, right? It would not be that hard. That's what MATLAB does.
So, yeah.
Do that at night. Other questions?
So there's nothing that we need. In that,
Never.
um,
MATLAB's a calculator. I never once said you need to use MATLAB. If I said that, how many people here are going to use MATLAB on their test?
More our playing on tomorrow.
No, but I'm saying, tomorrow, walking in the test, are you going to use MATLAB? Just
Sure.
so a few. But if I said you needed MATLAB, how many people would do it? Everybody, right? Yeah, no. because I don't want to, I'm not writing a test to see how smart MATLAB is.
Okay, sure.
I want to see what you've learned.
Well, you gotta.
You really don't, right?
No, you just good.
MATLAB is a calculator. That's all it is. It is. It's just, it's a nice tool to see all the information. I just encourage it because for me, what I truly believe is that you learn a little more when you use MATLAB. But again, when you look at the stuff that I put out here and you see it MATLAB scripts, you're like, it's all right there. You can actually see the process being worked out. When if I do it in my calculator, I put stuff on the slides and you can't necessarily see how those equations are entered, but MATLAB actually shows you that's how the data is entered. Any last minute questions? We've kind of exceeded our time, but I hope this was useful. Anybody in TV land with any questions?
Could you do another quick little overview of the R times 180 stuff with the N minus M?
Yeah, so the R, it's gonna be really quick, but R is gonna go equal to plus or minus 1, plus or minus 3. My computer works. And then all the way to N minus M. So you just have to allow R to approach the N minus M. It always has to be an odd number, but you can't ever exceed N minus M. We just one more minute per class. Thank you. Anything else? All right, have a great day, and I will see you all tomorrow at the test. Good luck, everyone. Take care.
Thank you.